What if a spaceship could push itself to Mars in a matter of days? Scientists are testing a radical new rocket that spins molten uranium to heat hydrogen, unlocking speeds once thought impossible. In this video, we'll explore how this breakthrough works, why it's so important, and what it means for the future of space travel. A fresh chapter in nuclear propulsion has just opened with the Centrifugal Nuclear Thermal Rocket, CNTR, a design that tackles old problems with a radical twist. Unlike traditional nuclear thermal rockets that rely on solid fuel rods, CNTR uses molten uranium fuel held in place by centrifugal force. By spinning the uranium at extremely high speeds, scientists keep it away from reactor walls, avoiding meltdown risks and allowing it to reach temperatures far beyond what solid fuel can handle. Here's where it gets impressive. The design allows hydrogen gas to be injected directly into the spinning uranium. The hydrogen rapidly heats to extreme levels and is expelled through a nozzle to generate thrust. Early simulations suggest this could yield a specific impulse of around 1,500 seconds. To put that in perspective, current chemical rockets average around 450 seconds, and even traditional nuclear thermal concepts only target 900 seconds. CNTR nearly doubles the efficiency of older nuclear designs and triples what chemical rockets achieve. This efficiency leap translates into mission-changing performance. A spacecraft using CNTR could carry more payload, burn less fuel, and, most importantly, slash travel times. Researchers emphasize that reducing transit time is critical for crewed missions to Mars because astronauts face constant radiation and microgravity hazards. A trip cut from months to just weeks could save lives and resources. The team behind the breakthrough validated their models through both computational fluid dynamics and scaled laboratory experiments. They confirmed stable liquid behavior under rotation and reliable heat transfer from molten uranium to hydrogen. With this step, CNTR moves from a bold concept into the realm of practical engineering. It's not yet space-ready, but the door has been opened to propulsion systems that could finally make fast interplanetary travel a reality. To appreciate why CNTR is so important, we need to step back to Project Orion in the late 1950s. Orion was one of the boldest spaceflight ideas ever proposed, a spacecraft accelerated by a series of controlled nuclear blasts behind a giant pusher plate. Each detonation would slam the plate, transferring momentum to the craft. On paper, this allowed payloads of thousands of tons and velocities high enough to reach Mars in about 10 days. Orion engineers even conducted subscale experiments in 1959, famously launching putt-putt models powered by conventional explosives. These tests proved that impulsive propulsion could be stable and controllable. Theoretical studies projected an interstellar potential as well, with concepts for probes reaching nearby stars within centuries. Yet Orion had one fatal flaw. It required actual nuclear explosions in space. After the 1963 Partial Test Ban Treaty, which prohibited nuclear detonations beyond Earth's atmosphere, Orion was effectively grounded forever. Fast forward to today, and CNTR emerges as Orion's conceptual heir. Both share the same ambition, massive payloads and unprecedented speeds, but CNTR achieves it in a continuous, controlled manner. Instead of external blasts, the power comes from a rotating molten uranium core producing sustained thrust. No nuclear detonations, no treaty violations, and far more manageable engineering. There are other parallels, too. Modern materials science and advanced simulations mirror the spirit of Orion's engineers, who worked with the tools of their time. Today's tools allow precise modeling of fluid dynamics, radiation, and thermal behavior, giving CNTR a level of predictability Orion never enjoyed. At the same time, laboratories like General Atomics are testing nuclear fuel elements under high temperatures, up to 2,600 Kelvin, with hydrogen exposure, showing the materials can survive the brutal environment that future reactors will demand. This evolution illustrates how vision from the past can merge with today's science to create propulsion methods that are not only powerful, but also realistic within regulatory and safety frameworks. CNTR may not look as dramatic as Orion's firecracker pushes, but its promise is just as revolutionary. The importance of this breakthrough cannot be overstated. Time is the enemy in deep space travel. Current chemical rockets require 6 to 9 months to reach Mars, depending on planetary alignment. During that time, astronauts are exposed to dangerous cosmic radiation and suffer from the physical toll of prolonged microgravity, muscle atrophy, bone loss, and immune system weakening. Shortening the journey isn't just convenient. It's critical for crew safety and mission success. CNTR's projected performance could cut Mars missions from months to mere weeks, possibly even days, depending on trajectory. That's transformative. It would also change launch schedules. Today, Mars missions depend on narrow 2-year windows when Earth and Mars align favorably. With higher thrust and efficiency, CNTR propulsion could expand or even bypass these windows, offering more flexible mission planning and increased opportunities for crewed flights. Payload capacity is another game changer. Chemical rockets like Saturn V could deliver about 140 tons to low Earth orbit. By contrast, Orion was projected to deliver thousands. CNTR sits between these extremes. While not as colossal as Orion, it far outstrips chemical and even standard nuclear thermal rockets, enabling larger habitats, more supplies, and more scientific instruments to be sent in one mission. The ripple effects extend to the outer solar system. Missions to Jupiter, Saturn, or even Neptune that currently take a decade or longer could arrive in a fraction of that time, unlocking science goals within a human career span. Probes could reach the ice giants while still operational and transmit valuable data before their systems degrade. From a strategic perspective, this also helps maintain momentum in human spaceflight. Programs like NASA's Draco project, aimed at demonstrating nuclear thermal propulsion, have faced setbacks and cancellations. A successful CNTR program could reignite investment and political will, offering a credible path to Mars and beyond. In short, CNTR isn't just about speed. It's about making deep space exploration practical, sustainable, and safe for humans. The vision of a spaceship that could push itself to Mars in a matter of days has long lived at the edge of science fiction. But with breakthroughs like the Centrifugal Nuclear Thermal Rocket, that vision is starting to feel possible. By spinning molten uranium and using it to superheat hydrogen, engineers have found a way to unlock efficiency levels far beyond chemical rockets and even traditional nuclear designs. If you enjoyed this video, don't forget to like, share, and subscribe for more updates, and don't forget to leave a comment below. Thank you for watching, and see you next time.